4.174 was dealing with the zip codes. And the first thing they did, they want you to look at the 5-digit zip code. And the first 4 digits can be anything from 0 to 9. So for our first digit, we have 10 options. For our second digit, we have 10. Our third digit, we have 10. And our fourth, we have 10. But then our last digit, our 5th digit, can only be from 1 to 8. So that only gives us 8 options here. Well, now when we multiply all those together, for part A, you will come up with 80,000 different options. Okay, part B wants to know how many of the plus 4 digit zip codes are there. Well, our first 3 digits can be 0 to 9, so I've got 10 for my first one, 10 for my second one, 10 for my third one, and then my 4th digit has to be from 1 to 9, so there's only 9 for that one. So part B, when I multiply all of those together, I end up with 9,000. And part C wants to know how many total zip codes are there if you consider the 5 regular zip code and the plus 4. So I would have to take my 80,000 times it by my 9,000, and you're going to get 720 million possible zip codes for part C. Okay, 4.178, similar type of problem. Now we are looking at phone numbers. So part A wants to know how many different area codes are there. Well, if I mark blanks for my 3 digits, I have 9 options for my first one because it can't be 0. And then I have 10 options for my next 2. When I multiply those all together, I end up getting 900 only for my area code. Part B wants to know how many local telephone numbers are possible. So now they're just looking at the 7-digit. And our first digit can't be 0, so we've got a 9 there, and all the rest of these have 10 different options because they can be any of 0 through 9. Multiply those all together and we get 9 million for part B. And then part C wants to know how many telephone numbers are possible. So this is including our area codes and our zip codes. So we need to take our 900 times our 9 million. And we're going to, oops, that comma should not be there. We're going to get 8,100,000,000. 4.187, probably the most challenging one on here. It's talking about 5-card stud. And we're going to be getting 5 cards from an ordinary deck of 52. Part A wants to know how many 5-card stud poker hands are possible. Now they tell you in the reading here that it's an ordered arrangement, so that's their way of telling you that the order does matter. So we want to deal with permutations. I'm going to be picking from 52, and I'm going to be picking 5 of them. And when you use your calculator to do 52p5, you're going to end up with 311,875,200. So that should have been your answer for part A. Okay, part B is the question dealing with how many different hands consist of 3 kings and 2 queens. So this one, we've got 2 different ways to look at it. First way I'm going to do involves actually combinations. So if I deal with my kings, I want to know how many different ways can I get kings. So I would do 4 combination 3. And that's going to give me back a 4. So that I have 4 ways of getting 3 kings. And then I'm going to do the same thing with my queens. I have 4 to choose from, and I want 2 of them. And that's going to give me 6 ways of getting queens. Okay, so once our suits have been determined, now we have to look at the order of them. So this part right up here was just determining which suits did I pick. Now we have to decide, how do I put them in order? Well, from those 5 cards that I'm picking, I have to figure out how many different ordered arrangements are there. So I've got 5 cards I'm choosing because I chose 3 kings and 2 queens, and I need to pick all 5. I need to put all 5 in an order. So I would have 120 different ways of ordering any of the 5 cards. So altogether, I'm going to have 4 times 6 times 120 because I've got 4 different ways of choosing 3 kings. I have 6 different ways of choosing 2 queens, and once I have that particular thing chosen, I have 120 different ways of arranging them. Multiply that together and you're going to get 2,880. So basically what this means, this top part here is saying I picked the King of Hearts, the King of Diamonds, and the King of Spades. So that would be one of these 4 arrangements right here. Then I'm also going to pick the Queen of Hearts and the Queen of Diamonds. That's one of this 6 right here. This 120 is saying how can I put these specific 5 cards right here in order? Well, I could have my King of Hearts, my King of Diamonds, King of Spades, Queen of Hearts, Queen of Diamonds. Or I could maybe have the King of Diamonds first and the King of Hearts second. So I have 120 different ways that I could take these 5 cards and rearrange them. So that's where all of these numbers come into play. Another way of thinking about it is using permutations to start with. So we are going to deal with the kings first again. So I've got 4 kings to choose from, and I need to pick 3 of them in a specific order. Well, this is going to give me 24 if you do 4 permutation 3. So this is saying how many different ways can I order my 3 kings. And then if I do the same thing with my queens, I would have 4p2, and that's going to give me 12. So this is saying how many different ways can I order 2 queens. Now the last part you have to think about is these 2 together, because the 24 right here only told me that, oh, I'm going to have the King of Hearts first, the King of Diamonds next, and then the King of Spades. It doesn't tell me anything about where the queens fit into this arrangement. So the last thing you have to think about is how many different arrangements can I put these kings in out of these 5 cards. So if I had my 5 cards dealt out here, I need to figure out how many different arrangements could I put my kings in. Now I'm not dealing with the order anymore because this 24 already decided which order they come in. I'm just looking at position. So did I draw a king first, second, and fourth? Or first, second, and last? Or first, third, and fourth? It doesn't matter which suit, we're just looking at the different number of arrangements. So to figure that out, I've got 5 cards that I'm trying to fill in, and I need to figure out how can I arrange 3 of them. And the reason I'm using a combination here is because we already determined the order when we did the permutations up here. So this is just looking at the arrangements. Well, when I do 5c3, I get 10. And now if I take my 3 numbers again, my 24 times 12 times 10, I still get my 2,880. Okay, part C of this wants to know how many different full houses are there. Well, we've got 13 different choices for picking our 3-card denomination. So we have 13, choose 1, which ends up being 13. And then we have 12 different choices for choosing our 2-card denomination, which would give us 12. And then take that 2,880 we had from the first problem. So we have 13 ways to choose the one that has 3. We have 12 ways to choose the one that has 2. And we have 2,880 ways to actually get the full house. Multiply those together and we get 449,280. And the last part wants to know your probability of getting a full house. Well, take our 449,280, our ways to get a full house, and divide it by that 311,875,200. And that gives us a probability of 0.00144. Okay, and the last one, we have the lotto problem. You have to select 6 numbers from 1 to 42. Ticket costs $1. To win, you must match 3 or more. If you match exactly 3, you win $2. If you match 4, 5, or 6, the payout depends on how many tickets were sold. First question wants to know, what's our probability of matching all 6 numbers? Well, remember our probability is the ways you can win divided by your total number. Well, the ways that we can win is we have to have 6 numbers to pick from, and we have to match all 6 of them. The reason I'm using combinations here is because the order that we pick them in doesn't matter. Now our total number of options, we have 42 numbers to pick from, and we are going to be picking 6 of those. So when you calculate those all out, you end up getting 1 over 5,245,786. If you wrote that out as a decimal, it's 0.1, 2, 3, 4, 5, 6. It's 6 zeros and then 191. So that's your part A, matching all 6 of them to get the jackpot. Part B wants to know, what's the probability that your ticket contains exactly 4 winning numbers? So again, we're looking at the probability. Our bottom number here isn't going to change at all. We still have that 5 million possibilities. But now I want to match exactly 4. So from my 6 winning numbers, I need to pick 4 of those winning numbers. But now you have to keep in mind, we also have to pick 2 losing numbers. Well, out of the 42 numbers, if 6 of them are winners, that means 36 of them are losers. So from those 36 numbers, I need to pick exactly 2. And then still divide that by my total. When you multiply that out, you're going to end up with 0.00180145. So that would be part B. Now part C wants to know, what's your probability that you don't win a prize? So let me erase all of this. Okay, so we're looking at probability again. Our total isn't going to change. It's still 42, choose 6. But now we have to look at our probability that we don't win. So we are looking for no matches. We are looking for 1 match or 2 matches. Because any of these 3 situations means we don't win. So for no matches, our probability, or not our probability, but the ways we can get no matches, we would have to have 36, because we're picking all losers, and we have to pick 6 losers. Now, technically, we would still have 6 winners, but we're going to pick 0 of them, and this turns out to be a 1. So we can kind of ignore that for this particular example. Okay, for 1 match, out of the 6 winners, I have to match 1, but then out of those 36 losers, I need to match 5 of them. And then for 2 matches, out of my 6 winners, I need to match 2, and out of the 36 losers, I need to match 4. So when you do this all out, the top one is 1,947,792. So that's how many different ways you can get no matches. The different ways to get 1 match is 2,261,952. And to get 2 matches is 883,575. Add all those up, and that's going to give us our top number up here. So when you take our top divided by our total, which is that 5 million that we already calculated before, you're going to end up getting 0.971. So basically you have a 97% chance of not getting a winning ticket.